than a billion floating point operations, right? So this is mind-boggling, right? And what has really powered this deep learning revolution so far has been the GPUs. They offer a lot more floating point operations per second compared to the CPU, which is much more general purpose. But again, this is only the beginning of this arms race to improve processing capabilities, and there are lots of startups as well going for more specialized hardware. Both NVIDIA and Intel are further improving their hardware. So there's also lots of exciting developments in this space. So let me now tell you at AWS how we are using this MXNet package and developing it. It's Apache open source, so it's usable by everybody, and how we can make it easy to run this on the AWS infrastructure. So you can think of MXNet as the deep learning engine, right? So that's what powers deep learning. And the term MXNet comes from mixed paradigm of programming. So the idea is there are two paradigms. There is imperative and iterative. I'll come to that in a minute. But most programmers or data scientists tend to write in Python or some very simple language, right? So you write it line by line and you try to say what you want to do. But in terms of performance, this is not great. And so what MXNet does is take this very simple program and converts it into declarative style that makes it possible to have high efficiency. You can run this on multiple machines, you can parallelize it easily, you can optimize for memory. So it's all done automatically, right? So you as a data scientist only need to write this code for saying what you want to run and not worry about the details of how it's enabled in distributed systems. So don't worry about what this program is exactly doing. I guess we can all agree that writing parallel programs in traditional style is painful. So I don't know how many of you took a parallel programming class, right? But the traditional programming languages like MPI are very low level. Like they're not, like every instruction you want to say, like where you want to send it, right? Where you want to buffer it. That is too much detail, right? I mean, here as you see, like often you may require up to thousands of communications even for one iteration of this algorithm. And so there is no way you can specify each of these iterations and say what you want to do, right? So the complexity is mind-boggling. So just to give a short idea of what this picture is showing is, there is our CPU and there are two GPUs. You want to send one chunk of data to the first GPU and the other chunk to the second, right? So you want to parallelize your data to your multiple GPUs. And each GPU does its own processing of data. That's what this forward pass here is doing. And so now once each GPU has done its own processing, it needs to send back. So it's sending this, communicating it back to the CPU, right? So this is, as you can see, pretty much a toy example, but what happens much more widely. You distribute your data, you get back information about updating the parameters of your network. And so how do we enable this at scale? How do we have this be very easy for programmers and at the same time have high efficiency? So one aspect is, as I said, to have, if you had like a graph that said what is the sequence of computations, you can have the back end automatically parallelize, right? So as I said, we don't want the programmer to write every instruction on how to parallelize. But if you have a graph, you can use some simple rules to parallelize automatically. So in this example here, these two operations can be done in parallel, right? So as you're traversing the graph, you can have some simple rules on when you can parallelize these operations and when you should do this serially. So having this graph will help us do the parallelization. Right? So as I mentioned, the most common form of parallelizing your operations is by parallelizing data. Right? So typically in these applications you have large amount of data. Right? So the ImageNet data set that I mentioned for images has more than 1 million examples. So you cannot process them all at once. You cannot process them in a single GPU. So what you do is you take mini batches. So you take small chunks of this data, push them out to each of the GPU, and each one does its own forward and backward pass. Right? That's the set of operations to update the weights of the network. And those are shared across, this key value store is the one, is in some server that coordinates and aggregates this information and then sends it back to the individual GPUs. And so this is done again and again. So I'll come to how we implement this in a second. But conceptually, this is the idea, right? So we distribute data across our multiple devices. Each one does its set of operations and then sends back the information to a central server. And that central server shares this updated information with everybody and does this again and again. So why this is so expensive is this is done thousands of times, right? Because you are chunking your data to because you have a huge amount of data, you can only send a small fraction of it into each GPU. And that's why you have to do this again and again. And that's why it's tricky to have efficient frameworks for this setting. And so in terms of where do we put this parameter server that aggregates information, right? So in the example I showed before, if you were communicating to the CPU, but again, that's a low bandwidth connection compared to communicating amongst the GPUs themselves. In fact, NVIDIA released their latest Volta GPUs and the numbers are even higher there. So they have very efficient GPU to GPU interconnect communication. And so we can exploit this hardware advances to do most of the operations right at GPUs. Right? So you only go up to the CPU if you want to communicate across the network or you want to take the data. But all the aggregation happens, like you designate one of the GPUs as a server and aggregate this. I mean, these are simple notions, but in practice, it has a huge impact because we are exploiting GPUs for what they're good at, right? So we're exploiting them for parallelism. They're extremely well optimized for these linear algebra operations that these networks run. And they're also very efficient for communicating amongst each other, GPU to GPU communication.
So you said you're aggregating the data at the GPU. Is that data the weights that each one is established for that pass?
It's the gradients of the weights, right? So in this operation here, what the GPU send will be the gradients, right? Because it's the gradient update that will tell you what the resulting weight is. And so the algorithm that's run is typically the stochastic gradient descent, right? So there is gradient information, and using that you update your weights. And it's very simple. Like stochastic gradient descent has been there forever. I don't even know where to trace it back to 60s, 50s, probably even earlier, right? So this idea of like you're descending according to the gradient is a very old notion. And so that's what I mean by the algorithm being very simple, but the implementation details matter a lot in being able to run these systems at scale. Yeah. So let me show you, there are so many experiments we've done, but I want to show you one. And this is on the ImageNet. As I said, it's about 1.2 million images, right? And the other challenge is also the number of classes. So this is more than 1,000 classes. So classes are categories, whether it's a dog, cat, rat, like all these categories of what the objects can be. And once you increase the number of classes, right, that's when the problem gets very hard. Because having the classifier distinguish what's a cat and a dog is much easier than categorizing within different dogs as well as distinguishing within different cats. Right? So you're increasing the number of categories, the task of machine learning gets harder. And that's why ImageNet is a very popular data set because of its scale. It has lots of data, but it's also asking you to solve a hard problem of learning multiple different classes. And as you can see, this ResNet is again one of the state-of-the-art networks. It has 152 layers. So these are, very large-scale networks, and we are running it on the EC2. The P216X large has 16 GPUs within the same machine. So these are the K40s, and very recently, less than a month ago, we released the P3s that have the Volta GPUs, and they're even faster than these older generation GPUs.